Hey, today at Flippin Science, we're looking at recycling and composite materials.
Gotta make some trash, but don't throw it out. Recycle. Gotta learn to recycle. We got 3 reuse, recycle. Reduce, reuse, recycle. Reduce, reuse, recycle. Reduce, reuse, recycle. Because 3.
So the science understands we're going to look at there's a finite amount of materials on Earth. Materials that can be recycled will reduce the amount of new materials that are needed to produce from the Earth's crust. Explain the advantages of recycling. And composite materials comprise 2 or more constituent materials to produce material with properties different from the individual components. Explain the advantages of using composite materials, and explain the difficulties associated with recycling materials and objects that are composite. So let's talk about recycling. There's a limited amount of materials on Earth. We do gain some material from space every year, but not much, and not enough to replace what we use. So we have non-renewable materials, and when they run out, they are not going to be replaced by anything, at least not in the scale of a lifetime. So some substances are very cheaply available now, but when the materials run out, they may be more expensive. So at the moment, we've been looking at polymers and plastics. A lot of them are produced from petrochemicals. Petrochemicals are reasonably abundant at the moment, but over time they'll become less abundant. Because of that, the plastics that we are using now will become more expensive unless we can find viable options rather than using petrochemicals to produce them. So by recycling materials, we can reduce the environmental cost associated with extracting substances from the ground, but we can also reduce the amount of waste going back into the environment, which would be beneficial for the environment as well. So let's look at metals to start with. So recycling metals reduces the environmental costs of metals. A great example is aluminium. So aluminium requires an awful lot of energy to produce because there's a lot of refining that goes into producing the alumina. But to reduce the aluminium ions, you need to heat up a molten salt to very high temperatures, and you do that using electricity. So you need abundant, cheap electricity to be able to produce aluminium. If you can recycle aluminium, you get rid of 90% of that energy cost. It's much better to recycle aluminium than it is to extract bauxite from the ground and turn it into new aluminium. So because of this, aluminium recycling is very, very popular because it saves a lot of energy. Steel is recycled very highly as well. Steel is used in a lot of places. It's used in construction. It's used all over the place. And you can recycle steel relatively well. So aluminium is pretty much infinitely recyclable. Once you use it, you can reuse it. Steel, you lose a bit when you do the reforming, but you still save about 60% of the energy cost. So you're reducing costs of energy, which is an important and big cost in industry, but you're also reducing the environmental cost of having to mine things. So you're not cutting into the ground, you're not displacing animals or plants, you're not damaging ecosystems if you don't have to mine the material when you can just get it from recycling rather than mining it. Now, some of these similar ideas apply for other substances that are metals, like glass and newspaper. For glass, you don't need to put as much energy into the refining process to make sure you have clean glass because you've already got the glass if you're recycling it. In terms of newspaper, you don't have to grow more plants in order to make more paper. So again, you're reducing environmental costs. In growing plants, you have to fertilize, you have to water, particularly in producing paper, there's an awful lot of water that goes into that process. So you don't have to use that if you're recycling materials. Now let's look at composite materials. So a composite material is a material that's composed of 2 or more different materials stuck together. The 2 materials often have different properties, so by combining those materials together you get a material with different properties than the initial materials that you started with. So a good example is a mud brick. So a mud brick is made from mud mixed with straw, and then it's shaped and it's left to sit. So by doing this you end up with a material, the mud brick, that is stronger than the mud or the straw. By combining the 2, you get a stronger substance that also has a bit of flexibility in it because of the straw than you started with. So there's many composite materials in nature. So wood is a good example. It's made of cellulose. So here you can see cellulose and hemicellulose, as well as another substance called lignin. So by combining those together, the cellulose or lignin by themselves aren't particularly strong, but by combining them together and making a decent structure out of it, you get a much stronger substance. Bone is another good example. So it's made up of calcium phosphate, which is a strong crystalline salt, and collagen, which is a flexible protein. So you get some strength and you get some flexibility, and you're combining those together to get a substance that is stronger than either of them would be by themselves. Calcium phosphate would be strong, but it would also be brittle. By putting in a flexible protein, you can allow the bone to move a little bit before it breaks. So you get advantages by mixing the 2 components together and sticking them together, which is what your cells do in your bones. Synthetic composites are very common as well. A great example is concrete. So concrete is made up of rocks and sand, which is often called aggregate. So you have a coarse, which is the bigger rocks, and then you have the fine aggregate, which is the sand. And you're sticking those together with cement and using water to do that, and other bits and pieces in there that you can do to make it cure faster, for example. So that's just the concrete, but then often that is combined with steel to make reinforced concrete. So here's concrete, that's the grey stuff, and here we have steel on the inside. So by combining these, steel which has a bit of flexibility in it, and concrete which has good compressive strength, you can make really big structures. So this is a photo I took in Japan when I was there. So this is the Sky Tree. So it's a really tall tower, it's got restaurants, shopping, it's got a nice observation deck up the top. So if you look at its structure, you can't really see much concrete, but that's what's inside these tubes. So these tubes have structural steel inside there, and concrete is poured into those tubes, and those tubes are joined together. You can see lots of triangles, which is a very strong structure in engineering. So this whole thing is reinforced concrete, and in Japan you need to have strength, but you need to have flexibility due to the fact that they have lots of earthquakes. So this is very strong, but it's also flexible. That means it can withstand very strong earthquakes. It will stand for a very long time. So to make a synthetic composite, you need to have a matrix, which is the thing that sticks everything together, and a reinforcement. So if we look at our example with concrete, the cement that is holding everything together along with the aggregate, that is the binder, the matrix, and the reinforcement that's in there is the steel. So we have the matrix, which was the cement, and the reinforcement, which was the steel. So we're combining something that's holding everything together with something that has a bit of flexibility to it. High performance composites, they're usually made out of a thermoset or thermoplastic polymer, and they're reinforced with fibers. And those fibers can be made of glass, carbon, or they could be made of metals. Here we have, say, fiber reinforced composite, and we can see we've got the matrix on the outside, that's the polymer matrix, and then we have our reinforcing fibers on the inside, so our reinforcement. There's many examples of this. So here's a fiberglass boat. So a fiberglass boat is made up of a plastic of some kind, it's usually a resin, and inside there is glass fibers, and those glass fibers provide flexibility, and the resin provides a bit of strength. So by combining those two together, glass by itself would smash, but by putting it in plastic, you make it nice and strong. So you can make things like boats and all kinds of things out of fiberglass. So carbon fiber reinforced polymer, CFRP is how it's normally referred to as, but we normally just call it carbon fiber because it's easier to say that. It's very light and it's very, very strong. So because of that, it's used in lots of applications. One of the problems with it is it's quite expensive too. So because it's expensive to produce, it hasn't made its way into daily life for everybody yet, but it is present in lots of very expensive applications, and we'll talk about some of those shortly. So it's a matrix of polymer, so it's usually an epoxy resin, which is a very, very sticky plastic, a polyamide or a polyester, these are just plastics, but inside there you have carbon fibers. Carbon fiber there's lots and lots of carbon bonds through there, and they're reasonably strong. So you mix the carbon fiber with your resin, or your plastic, your polyamide or your polyester, and you get a very, very strong substance, which is the carbon fiber. So you can see the carbon fiber over here, it's being woven together. Once it's woven together, you shape it into the shape that you need it to be, and then you pressure cook it. So you heat it under pressure, and it retains that shape. And it's very, very strong, but also very, very light. So because of that, it's used in many applications. So if you're lucky to have flown internationally out of Australia, you might have flown on a Boeing 787 Dreamliner. It's about 50% composite, and a decent amount of that is carbon fiber. So we can see carbon laminate, carbon sandwich, and other composites. The reason why it's being used in the plane is this makes the plane lighter because you don't have to use aluminium, which is a strong metal, but it's also heavier than the carbon composites. But because it's lighter, you don't have to push as much in the air, so it uses less fuel. So these things are reasonably fuel efficient compared to other planes that are made out of pure aluminium. Here we have a fancy Porsche. You can see the carbon fiber, it's that black color. It's very popular in cars even when it's not really carbon fiber, it's just plastic that's made to look like it. That makes the car lighter. And again, in racing, you need to have a very light car, because the lighter it is, the faster it will go around the track, but it's also very strong, so you can protect the people inside. Carbon fiber is being used in bicycles. Again, you want it light so you can go faster, and in tennis rackets and other applications where lightness and strength is important, but also money isn't much of an object too. So you need to kind of have both of those things going on. Now, the problem with composites is because they're made up of at least two substances, it's very tricky to recycle them because you need to separate those two substances that make it up. You need to separate the matrix from the reinforcement. If you're using thermoset polymers as your matrix, it makes it very, very difficult to recycle your composite because you can't just melt it. If you use a thermoplastic polymer, then you can melt that and it makes the recycling much easier. There are methods to try and recycle composites, and I've got some examples down here. So you can use mechanical systems, which is where you crush things up and separate them out. You could use heat, so that's the melting the thermoplastic polymer, so that's down here, so they're doing that with the carbon fiber reinforced polymer. You can also use chemical systems. So over here they're using acetic acid and acetone. That breaks down the matrix, and you're left with your matrix separated out from your carbon fiber. And then theoretically you could recycle that. Composites are difficult to recycle because you've stuck two different substances together and you need to separate them out from each other, and that can be tricky to do. It can cost a lot of money. The quality of the separated components isn't necessarily the same as the virgin components, and there's not really much infrastructure to do this at the moment. So not much of this is happening. So at Flipping Science, we looked at recycling and we looked at composites. That's it, Flipping Science today. See ya.